In this lesson we will see the KNN, which is a supervised ML approach, and then we will move to the unsupervised learning looking at the clustering in particular. Finally, we will conclude our discussion dealing with simulated data for validation purposes. KNN is a nonparametric supervised learning approach, where nonparametric means that there is not a model to fit through its coefficients, while on the contrary the data are directly used without the formalization of a model. This gives flexibility to the description, which does not depend on the assumptions made to structure the model. In the KNN, the input variables of each observation represent its coordinates in multidimensional space. Each point has an associated label in the past observations. The goal is to predict the label of a new observation, which is also modeled as another point in the multidimensional space. The estimated label for this new point will be that of its closest neighbor points. The distance can be the classical one, Euclidean distance, that of the Pythagoras theorem, but other distance metrics can be employed as well. The approach can be tuned by deciding the number k of points to include in the neighborhood of the new point to evaluate. For example, we consider k equal to 5 points in the example of the slide. The estimation for the new point, in the case of classification, is the label of the majority of the points in the neighborhood. Usually, an odd number is chosen for k to avoid ties. For regression where the label is a number, the estimate can be the mean or the median among the points in the neighborhood. We now consider a practical example. Observations are characterized by two input variables and by a binary label, bad or good. The goal is to predict the label of the fifth point based on the other 4 points. We can report all points in the plane, which is our multidimensional space with only 2 input variables. Now we compute the Euclidean distance of the new observation, denoted by point P5, from all others. This is simply the Pythagoras theorem in the plane. If we choose k equal to 3, the 3 closest points are P1, P3 and P4. The label is good in 2 out of these 3 cases. Therefore, our prediction for the new observation is good as well. Therefore, we can complete the table with predicted label equal to good. We recall now the figure we have seen to discuss unsupervised learning. This shows that, as previously mentioned, in unsupervised learning there is no label associated with the observations. But the purpose is to regroup observations that are similar to each other, or better, to cluster them. More specifically, unsupervised learning refers to algorithms that learn patterns from untagged data with no label, without an explicit model as in regression or neural network. These approaches do not need a training and are not used to predict the output of a future observation. On the contrary, they search for relationships within a given dataset in which no new observations will be inserted. Let us consider, as in the KNN, the observations as points in a multidimensional space. Here the goal is not to predict a label but to aggregate observations into groups, called clusters, where points within each cluster are similar. But what does similar mean? This means to minimize the distances between points within any cluster and to maximize any distance between points in different clusters. An example can be that of bioimage segmentation. Here the goal is to divide the image into its regions. There is not description of the regions, there is no label, but only similarity between pixels of the same cluster. From the above description it can be seen that clustering is similar to KNN. Why is it unsupervised? Because, let's stress this point, there are not labels associated with the observations, but only the features, input variables, of the observations. A common example of clustering is the so-called k-means approach. When the problem is complex, it is also useful to first use simulated data. The goal is to test the model fitting in a controlled environment. Therefore, once the structure of an ML model is proposed, the overall process is to first validate the model on simulated data and then validate the model on real acquired data, also performing cross-validation. This diagram shows how to deal with simulated data. Once the structure of a model has been defined, realistic parameter values are assumed, at least as regards their order of magnitude. Thus, with model equations and the relative parameters available, it is possible to generate simulated fictitious observations, using the model itself. Later, it is possible to forget about the assumed model parameters and, based on the simulated observations, the coefficient fitting is performed. Finally, we can compare the estimated coefficients with those we had assumed at the beginning and see how much they differ. This analysis allows to consider the effectiveness of the ML estimation approach and to answer to some questions such as: is the set of coefficients identifiable? Is the approach suitable? However, this analysis assumes that the model perfectly describes the real phenomenon and the real data, observations, are mathematically generated considering the same model. However, this analysis neglects the gap between the model and the reality. Each model is an abstraction of reality, which includes assumptions and simplifications. This analysis is only preliminary, devoted to assess the technical functioning of the modeling and estimation framework. Then, the model can be validated on real acquired data. This analysis includes the gap between the reality and the mathematical description. The best is to consider the cross-validation approaches above studied. However, if the results of this validation are not very satisfying, we need to analyze the reasons. And to this end, the so-called in-sample validation can provide useful insights. This is a validation for which there is not distinction between training and test set. And the same data are used both to train and calculate the errors. For example, if the in-sample validation is satisfying but the cross-validation is not, this could mean that a larger number of observations are required but the structure of the model and the approach are appropriate.